Sorry for the delayed start. I had another meeting. Hope you're able to hear me.
Yes, sir. Yes, sir.
Okay, very good.
Yes, sir.
So I'll start sharing my screen. Are you able to see my slides?
Yes, sir.
Okay, very good. So, good morning again. How's the connectivity and others? Anybody having any issues connecting or with Microsoft Teams? Is everybody comfortable?
Yes, sir.
Okay. Anybody with issues? Okay, that's nice to know. So I've been posting edited forms of these videos on YouTube as well. I hope you've been getting access to that because I've been posting the links on the chat box. Anybody not able to access those? I think everybody's fine. So let's get going. So today we'll be covering a few things regarding the distinctions that we talked about in the previous class in terms of both flight vehicle structures vis-a-vis other kinds of structures, as well as this particular course in terms of the direction in which we would take this forward. Okay. And we'll also talk about certain basis for classifying aircraft structures and the way we analyze or design them. So certain broad outlines towards that so that it will help us going forward. Some of you had mentioned that the contrasts weren't good in the previous slideshow, so I've tried to modify that. Hopefully this should look good. So I'll just does anybody want to say something, or otherwise just mute your microphones? I'm hearing some noise from one of the students. Okay, thank you. So we'll just go through that particular slide where some students had an issue with the contrast of the fonts over the slide background. So the last slide that we had in the previous class was about fundamentals and the 5 Fs that are specific to this particular course, the way it is conducted as opposed to any classical flight vehicle structures course in an undergrad program. So these 5 Fs is what will kind of distinguish it in some form over a typically undergraduate course. So as I said, this is a course predominantly for non-aerospace engineers to get up to speed with aerospace, but nonetheless we do not want to leave those of you with the aerospace background as well, and also those who want to specialize in structure. So these 5 Fs are the things that will be essential for those of you to understand in detail, and even for the non-aerospace, non-structures people, it will be important to understand at least the terminology involved. So the first fundamental that we are looking at is materials. We started off by looking at composites in the previous class because they are occupying almost 50% or more of the weight of the structure these days for most newly designed vehicles. So that's going to be kind of a way forward. In terms of volume fractions, it's almost 70% or more because of their lower density. So that's the kind of incorporation of composites we have. Can anyone of you say if the contrast is slightly better in this with the green and the black background?
Yes, sir. Awesome. Contrast is awesome.
Okay, great. Thanks. So the second fundamental that we need to cover, and these fundamentals are what will occupy most of the course. Okay, so the 5 Fs would be just like spice added, toppings added to dish to make it more effective and more current state of the art. But these are the building blocks over which most of the course will be dealt with. So after we look at materials from the perspective of light vehicle structures, we will review the theory of elasticity, talking about the stresses, strains, and the relationship between them. Then we'll go into looking at failure of isotropic materials, which are still used in aerospace engineering structures, but also to some extent the understanding the nitty-gritties of the composite failures as well. Then the predominant portion of this course will be in understanding beams and shells. So it will be kind of a extended version of the strength of materials courses that you would have taken. But in particular, we'll be focusing on thin-walled structures, and shells probably would have not been exposed to much. But we will see to what extent, without going into too much of the mathematical complexities of the modeling, how we can cover that as well. But thin-walled beams, by which we mean one-dimensional structures which could take not only bending but also extension. In other words, what you generally call as bars will also be treated as beams, and what you call as shafts, which take torsion predominantly, will also be dealt with as beams. So when I say beams, I generally mean any one-dimensional structure whose cross-sectional dimension is very small compared to the length of the beam in a statics problem, or compared to the wavelength of the most dominant eigenmodes in the case of a dynamic problem. So if you don't understand some of these terminology, hold on. As we go, we will introduce them in a little more concrete way. So as I said, these beams and shells can in general be subjected to a combination of extension, bending, torsion, and shear. So some of the models that we'll be considering will be linear. So if we can consider each one of these separately, and we can use principle of superposition to put them together. But when material nonlinearity or geometric nonlinearity set in, then you would not be able to do that. So you have to take all of these loadings upfront. Whatever loading is appearing on a particular structure has to be taken upfront. You can't do them individually and then try to add up the results for the stresses or strains or even displacements. What do we mean by material nonlinearity? It basically means that the stress-strain relationship is nonlinear. In other words, the Young's modulus, which relates the stress to the strain, changes. So it not only changes from one direction to another as in a composite, that's called anisotropy, but material nonlinearity basically means that the derivative of the stress to the strain in any particular direction need not be a constant. So in other words, the stiffnesses are changing with the deformation. So that is something called as material nonlinearity for our purposes. There are other forms of material nonlinearity as well in other physics. Next, going to geometric nonlinearity, it's basically the nonlinearity in the strain displacement relationship. So you typically have, let's say, for example, a translational strain in the x direction defined as epsilon x equal to dou u by dou x. That's a linear definition because there's a linear relationship between the derivative of u and the strain. So that's a linear strain displacement relationship. That's called geometric linearity. But in most aerospace structures, because they are thin-walled and also because they could be thin shells or plates, you would have geometric nonlinearity. In other words, you do need to take into account the nonlinear terms in the strain displacement relationship. Some of you would have gone through that in the initial portion of some of your elasticity or structural mechanics courses, but not taken it farther enough. But we do need to do that in the case of aerospace structures. Otherwise, we'll be far away from reality. Then we will talk about the 5 Fs. The first F, as I said in the previous class, is about fiber reinforced composites. As I said, even commercial aircraft are using it to a large extent, be it the Dreamliner from Boeing or the Airbus 350 extra wide body from Airbus. And this has resulted in more than 35% structural weight savings, which means that they are going to be the thing to stay on for a long period of time. So we do need to understand this, whether we are structural engineers or not. And the reason why we need to study it separately is because they behave very differently from the conventional materials that you are familiar with, especially metals. So we need to understand not only their failure, but also their behavior even before failure, which is quite different. For one, they are non-homogeneous. In other words, their material properties change from point to point because they consist of more than one material in a macroscopic sense. For example, the fiber and the matrix, which have very different properties. And the second aspect is anisotropy, which means that they have different properties in different directions. So how do you deal with them is what we will look at in a part of this course. The second F that makes this course a little more involved than an undergraduate course is the brief introduction to fracture mechanics that we will have as an essential tool for composite structure damage tolerance, because most designs today are damage tolerant designs. And this is important not only for the aging flight vehicle structures in understanding what is their life estimate or extending their lives even, but more so for the new non-deterministic designs that we talked about in a little more detail in the previous class, where the material properties are uncertain, the geometries could be uncertain, the model parameters could be uncertain, and therefore we need to look at that. So it's very important for students as well as professional engineers working already in the industry to get exposed to fracture mechanics. And then the third F, apart from fundamentals, that we'll be looking at is fatigue. In fact, many of you pointed out that one of the fundamental differences between aerospace structures and, let's say, civilian building is more in terms of the dynamic loads. And many of these dynamic loads can take the form of a cyclic loading situation. And these cyclic loading situations can result in fatigue. We talked about a very classic example in the previous class where we saw that the aircraft wing, because it's undergoing a lift, therefore it's bending upwards. So the top skin, for example, undergoes compression, and then when it comes down and lands on the ground, it's basically the self weight, which means it's going through tension. So this is basically a low cycle fatigue, but there are many high cycle fatigues as well. In other words, higher frequency at which this can happen, because there is vibrations that are involved because of the loading that is there, coming not only from the air loads but the other loads that we will see shortly. So this fatigue becomes critical aspect for durability, because if you have a static load, you know there's a certain level of strength. That strength goes on reducing as the number of cycles of loading increase in what is known as a typical SN curve that we will take a brief look at much later in the course. So the critical aspect for durability of composite structures is fatigue, understanding of it, and because they are loaded dynamically. The fourth complication that we bring in is in terms of finite element analysis. These finite element methods have become kind of the mainstay of analyzing as well as designing composite structures, or even metallic structures or combinations thereof, including their joints, etc., so that we can deal with not just those beams and shells that I talked about in the beginning in the fundamentals, but their combinations, which is what makes up a wing. For example, a wing is made out of panels which are on the top and the bottom of the airfoil cross section, the wing, and then those panels are then reinforced by those beams, which some of which we saw in the cutout pictures in terms of spars, in terms of stringers and transverse stiffeners like ribs. So such combinations, it's very difficult to deal with analytically. So in those situations, you do need to go for a numerical approach, and there the finite element analysis plays a critical role. So many simplified ad hoc techniques are no longer required, which used to be the main content of previous flight vehicle structures courses. So we are shifting the emphasis from a problem solving drill, which is what it used to be in earlier conventional courses, to developing the engineer's ability to better do these following three things. One is to understand the mechanics, what is the physics going on behind, how is it mathematically involved, and understanding that gives a lot of insight both for the analysis as well as the design, and makes our life much easier in terms of making certain decisions. Then also to formulate the problem. How well are we able to formulate the problem? Because that's half the solution process. If you haven't defined your problem well, then the solution is of no significance at all. And even if you have defined the problem well, is it defined well enough to go for an efficient solution? So the same correct problem definition can be in multiple ways, as we shall see, and therefore it's essential to define it in such a way that we can come up with the most efficient solutions. And when we come up with the results from a finite element software post-processing, we need to be able to judge its correctness. So these three are the abilities that we really want to develop here, instead of going into the very details of the finite element, how the coding, etc., which you will learn through dedicated courses for finite elements, nonlinear finite elements, etc., both in our department as well as civil and mechanical engineering, for those of you who are interested in taking this further. The final F that makes this course more of a grad course than an undergrad course is the exposure to flutter. And as an example of aeroelastic instabilities and buckling, which is basically an elastic instability, because failure that we saw earlier through fracture mechanics, for example, or even fatigue failure, could lead to material failures, whereas here we are talking about a geometric failure. In other words, because we have thin-walled beams and thin shells, those are prone to instability, especially under compressive loads. And these compressive loads need not be actual compression in a bar, for example. It could be bending, where in the case of the wing, when the wing lifts and therefore bends upwards, and therefore the panels on the top surface of the wing will be undergoing compression. So there can be local buckling that is happening there. Some kind of wrinkling could happen, and we do operate beyond these buckling loads in many situations, even in passenger aircraft. May sound scary, but there's no danger to the wing or the aircraft as a whole. So these are well studied and well documented things, and actually used on flying aircraft today. So we will look at examples of these elastic and aeroelastic instabilities. There are also static aeroelastic instabilities like divergence, which we'll touch upon. The reason why, again, this is important is they strongly influence not only the detailed design, but the preliminary design itself. In some situations, we want to avoid it. In some situations, we want to take advantage of it. For example, in certain maneuvers, we do want to design the aircraft, for example, fighters, that they are unstable in certain modes, so that you can maneuver them much better than you would a stable aircraft. Because if the aircraft is too stable, then a lot of maneuvers would not be possible. So it's always a trade-off between these, especially for such high demand aircrafts like fighters. So these phenomena need to be understood, all kinds of instabilities, because we might design it very well for material failure not to occur. But if a geometric failure occurs, again, it could be a problem. So these phenomena need to be understood from that perspective. As I already mentioned, these can be taken advantage of in some cases, like the advent of large rotors. These are important even in ground-based structures. Like, for example, you would have seen when you're driving on a highway, some of these long trucks taking long blades, which are basically rotor blades for wind turbines. And wind energy is something which India is investing a lot in, apart from solar energy. And you would see that these wind turbine blades are massive, very, very long structures, and many of them are made out of composites. And they have soft blades. So in other words, they are allowed to bend in order to improve their efficiencies, or even twist. So in such situations, we need to understand how to take advantage of some of these things. One is, of course, to avoid the instabilities like flutter, which could be damaging. But can we take advantage of, for example, the twist bending coupling? So when the blade pitches, whether it's a wind turbine blade or a helicopter rotor blade, how it changes its flapping features or a lead lag feature in terms of the bending can actually be utilized in making the helicopter or the wind turbine perform better at more higher efficiencies. So this is what is called as aeroelastic tailoring. You tailor the geometry of the composite layups in order to arrive at something which is much more efficient. In fact, we do this even not only for aeroelastic tailoring, but tailoring in general for strength and stiffness as well, as we shall see when we deal with fiber reinforced composites. And this kind of aeroelastic tailoring can lead to twist bending coupling to shed wind turbulence loads, which means that we are reducing the possibility of a flutter, or delaying it, or even completely avoiding it in the flight regimes that we are designing this vehicle for. So now that was just a kind of a revision from the previous class. Now we will see how we are going to handle these 5 Fs in this particular course. So these 5 Fs are distinguishing factors not only for flight vehicle structures, but for the coarse flight vehicle structures. So how we are going to approach this, because each of this is a big body of knowledge by itself, whether you're looking at books written on this, or journal articles, or even current state-of-the-art research going on presented in conferences. You'll see a lot of literature related to each one of them. So we don't expect all students to necessarily go through all that. So we will just follow your textbook, which is C.T. Sun's Mechanics of Aircraft Structures, in just giving you a taste for all of these, and so that you're not kind of left out in discussions in an aircraft design bureau or analysis bureau that you might work on later on in the industry or in academia. So let's look at the first two, that is, apart from the fundamentals, the fiber composites. So the approach that we will take in this course, and which is also what is there in your textbook, is that we will understand the constituents of the composite material, which means predominantly we don't use particulate composites except in rare situations, which is commonly used in automobile industry, etc. We use mostly fiber reinforced composite, because the purpose of using composite is to have the required strength and stiffness with the lowest weight, and fibers have very large strength and stiffness for reasons that we will very soon perceive. Predominantly it's because as you reduce the diameter of, let's say we start with a rod. We start with a rod of a particular isotropic material, and then keep on reducing the size of the rod that we make in terms of its cross-sectional dimension, but keep the length the same. So basically the diameter to length ratio of this rod keeps reducing in the manufacturing process itself. Then what happens is, as you go to thinner and thinner rods, that is ones of very low diameter, you basically are moving away from being a rod to a fiber, something like our hair, right? So in such situation, what happens, it becomes very flexible in bending, but it becomes more and more stronger and stiffer in tension. The reason why this happens is that defect density reduces. In other words, how many defects do you have in the material a priori per unit volume, that starts reducing. reducing, and therefore it becomes stronger and stiffer in the fiber direction. So that's the reason why we go for fiber reinforced composites as opposed to particle reinforced composites or many other forms of composites that you can have. Also, we rarely go for chopped fibers except in certain secondary structures. It's mostly continuous fiber reinforcements, which means very long fibers which are not randomly oriented but oriented in a particular direction for a particular purpose. So we will study the properties of those fibers, we'll study the properties of those matrices, what happens when they both come together, why are they essential. First of all, why do we need a matrix, why do we need a fiber, and how does stress transfer takes place between these two, and what are the typical candidate fibers and matrices that are used in the case of aerospace structures. We saw a generic example of that when we dealt with example aircraft in the previous class, where we looked at let's say carbon epoxy or glass epoxy, Kevlar epoxy, etc. And that's something that you're apparently doing as part of your homework as well. But we'll try to look at it in a little more detail in terms of these materials, their properties, and when they are used and why, so that you kind of have a confirmation of what you are doing for this particular assignment and take this forward in terms of a learning. So those mechanical properties which are of significance will be covered there. Then we will look at the constitutive law. So this is where a fundamental difference comes up, because as I said, composites are non-homogeneous and anisotropic, because of which you don't have a simple stress strain law like sigma is equal to E into epsilon, where E is a constant in any direction at any point in the material, which is valid for a metal. But even in metals, you know that the Poisson's effect is there, and therefore the stresses and strains which are normal are related in the three orthogonal directions. This is taken a little further, and you could have coupling with the shear strains also. You know that the shear stresses and strains in the case of a metal are not related to anything else. In other words, you just have, let's say, the shear stress tau just being given by G times the symbol that you typically use for the shear strain, let's say gamma. So that kind of a relationship that you have, where G is the shear modulus, a linear relationship, may not be valid. And even if it's linear, it might get coupled with the normal strains or the shear strains in the other direction. So these are the things that we need to be exposed to. And then we have to go one level further, not only from the fiber matrix and their combination into a single layer, but stacking up these layers, because in each layer fibers are going to be in one direction, or if it's a fabric that you're dealing with, it could be in two or more directions. But at the same time, you want to strengthen it in all the directions in which the loads are expected in the actual structure into which this material goes. So when you're trying to do that, you have to deal with what are known as laminates. Laminates are layers which are stacked upon each other, bonded to each other through various manufacturing processes like pre-pregs in an autoclave, or through RTM, which is resin transfer molding, or vacuum assisted resin transfer molding, etc. Various manufacturing processes through which these are stuck to each other, and these could have fibers in different directions, and therefore how do you deal with that? So then we come to the non-homogeneity becomes even more, because within a layer there is non-homogeneity because you have fibers and the matrix in between. Now you're talking about another level of non-homogeneity, where between two layers you have fibers in different directions and probably different volume fractions as well. Volume fraction is how much of fiber you have in the total volume of that, or how much of matrix you have in the total volume of that layer. So now and you could have different fibers in different layers, what is known as a hybrid composite, an example of which we saw in the Dhruv's main rotor blade in the previous class, where we mentioned that there is a little bit of carbon fiber epoxy which is included closer to the root of the blade, whereas most of the rest of the blade is made out of glass fiber. Here there's both the carbon fiber as well as the glass fiber. So you have a hybrid composite like that. So all all these non-homogeneities, and then the non-homogeneity coming because of multiple layers being stacked in different directions, you have to go for what is known as an equivalent homogenization. So you have a real structure which is non-homogeneous, but for modeling purposes, what is the equivalent non-homogeneous equivalent homogeneous model that you can have? So in other words, if you have a imaginary material which is having certain properties, so that if you take those properties as a function of the properties of the constituent materials, fibers, matrix, and the angles at which each layer is laid up, then you come up with the equivalent homogenized properties of the laminate. And that serves a whole lot of purposes, both in analysis and design, even in detailed design. But you always have the opportunity to go back and understand in the actual non-homogeneous structure what happens later on if necessary, which is essential typically when you're trying to deal with damage mechanics. So that's what failure is all about, damage mechanics, in terms of the failure of the material. But then you have the failure of the geometry also, as we said, because of elastic instabilities like buckling and aeroelastic instabilities like flutter or divergence. I might sound a little repetitive for those of you who are familiar with this, but it's essential to repeat this terminology, especially for those who are new to this aerospace engineering field, so that they get used to some of these terms, because once you understand these terms from different perspectives, then it becomes easy when you actually go into the mathematical models of understanding them. So bear on with me for those of you who are already familiar with these topics. So in this category, we'll be looking at strength criteria, because that's the way failure is defined for most materials, especially isotropic, and we extend that to the situation of composite materials. Then because of which, when you have loading in multiple directions, you will end up with what are known as failure envelopes. In other words, on a stress plot, let's say sigma 1 in the x1 direction and sigma 2 in the x2 direction, if you plot this, you know what is the failure limit. In the case of sigma 1, it can go up to a particular level. In the case of sigma 2, you know in the transverse direction it can go to a different level if it's a composite, and if it's a isotropic material, to the same level there as well. But now if you're applying in both directions, let's say tension in the x1 direction and tension in the x2 direction as well, it might fail at a load which is much lower than the ultimate or yield strength in those two directions. So in such situations, we need what is known as a failure envelope. So when we plot sigma 1 versus sigma 2, we get a curve, and this curve shows that if you are operating within that curve at stresses which are lower than that, then you are having a safe structure. The material is not failing, but it could still fail through buckling, etc. Then if you're above that, then it means that there are chances of failure. So these are what are known as the failure envelopes. So that's the way we'll be handling this to some extent in the course. The other things that we'll be looking at as part of failure and buckling is that the elastic instabilities, including thin columns and sheets. You are familiar with the Euler buckling, for example, pi squared EI by L squared for simply supported columns. So we'll try to extend that to some extent in thin columns, where the EI has a certain way of defining. You would have studied how to calculate the moment of inertia for I sections, etc., C sections, etc. So those are going to be contributing here, but the direction in which it could be unstable is basically the one in which the bending stiffness is the least. So it has a more proclivity towards that. But then again, it could depend upon the kind of material distributions, the boundary conditions, etc. Then more importantly, it's the sheet buckling, because as I said, we allow the panels of the top surface of the wing, for example, to buckle and still operate. So therefore, how they operate in the post-buckling regime is very important as far as these sheet metals or sheets of thin composite laminates are concerned. The next thing is one level up when we talk not only about the elastic loads but also the aerodynamic loads. Both in combination can get coupled with each other and create an instability in statics like divergence or in dynamics like flutter. And this again will be illustrated with the simplest possible models again only if time permits, because there is a specific course related to this. The third thing...
Excuse me, sir.
Yes, please go ahead.
Sir, this is Vanshik Dubey.
Yeah.
Sir, I had a doubt. Sir, modulus of elasticity
Yeah.
is a material property. No?
Correct.
So, is it constant we take constant for all the calculations. So, is it constant for homogeneous and isotropic material only, or all the materials?
Yeah. See, these are two different things. One is homogeneous basically means it's a point property. Anisotropy is also something related to a point in different directions. But Young's modulus basically is a material property, as you said rightly. But for small strains, it is constant for most materials. But as you increase the strain, what happens is if you plot the stress versus strain, the slope of the curve can change. For example, the typical situation you could have is, let's say, rubber kind of a material where as you start extending the amount of force you need to extend becomes different from what it was even to accomplish a unit strain. So this change in this load or stress required to create an additional unit strain is what is basically a changing E. So in other words, E becomes a function of epsilon. So E is no longer a constant. So in other words, if you write sigma, it becomes generally a function sigma of E, sigma of epsilon. And to start with, the leading approximation to that would be just E times epsilon. But there would be additional terms which are added, and that can in turn be incorporated within E by differentiating this equation sigma equal to sigma of epsilon, dou sigma by dou epsilon in a particular direction would give you E, which is a function of epsilon. So to start with, for very small epsilons, very small strain that is, you would have E constant, but then it would start varying. So that is what, and that can happen irrespective of whether it is homogeneous or non-homogeneous, or whether it is isotropic or anisotropic. So these are three totally different behaviors. One is linear non-linear behavior, the other is isotropic anisotropic behavior, other is homogeneous non-homogeneous behavior. This homogeneous non-homogeneous is basically from point to point differences. This is at a point in different direction behavior. Now this is at a point in a given direction, but changing with the increasing strain. So these are three mutually independent behaviors or types of behaviors that you can have either in a composite or even in metals. For example, if you have the crystalline structure or grain structure, grain boundaries defined in a particular way. For example, we go for what are known as single crystal structures for turbine blades. So in such situations, you could have the property along the blade length to be much superior to the transverse direction. So it is possible to have something like that. So these three are just defining the behavior of the material. Did I answer your question?
Yes, sir.
Yeah, thank you. So next F that we need to deal with is fracture mechanics. How do we deal with in this particular course? We go to the simplest way of handling it, because again it's a whole body of knowledge by itself. Fracture mechanics has been around for many decades now, very advanced for metals and kind of picking up for composite structures as well. So here the most basic concept, which is very systematic in its nature, is Griffith's concept of strain energy release rate, which is abbreviated as SERR. strain energy is basically the energy which is stored in a structure which is loaded mechanically. So there is a certain level of strain that it develops. Because of that strain, it is storing that energy that you're doing, the work that is done by applying a load on the structure. So if this is a wing, let us say, and I'm applying a particular load, that load into the displacement in the direction of the load at that point is the amount of work that I'm doing. So where does that work go? Predominantly it goes into being stored as the strain energy of that system. So when I remove that load, that strain energy is released. But that strain energy can also be released not by removing the load, even when the load is there. When, for example, within the wing there is a crack. So once there is a crack, there is a strain energy which is released, and there is a rate at which it is released. And rate here doesn't mean in this, usually we say, when we say rate, we say with respect to time, but here it is the rate with respect to which the crack grows. So for example, if the crack is length is defined as A, and the strain energy is denoted by U, then as the A increases, the crack size, the crack length increases, how much does the strain energy change? That is basically what we define as the strain energy release rate. That is dou U by dou A. The partial differentiation of the strain energy, which is a scalar quantity, with respect to the crack length, which is A. So new crack surfaces can be created, and per crack surface, as the crack length changes, how does the strain energy change? So this concept is very, very critical, not only for metallic structures, which is what Griffith actually introduced it for, but extending it, extrapolating it to composite structures as well. So we will look at how that is done in a very, very preliminary mathematical modeling, which may not be actually suitable, but will introduce you into concepts and terminology related to that. So what this will do, because there are many other ways of approaching fracture mechanics, like stress intensity factors, etc., which we'll also probably touch upon. But when we try to get a gateway into fracture mechanics through this concept of Griffith and strain energy release rate in particular, then we can take benefit of the global nature of this concept and the relation of this to the change of the total strain energy before and after crack extension. So that, in other words, there is a given crack, let's say it's of a constant length, then as the crack length changes, what is the original strain energy, what is the new strain energy now at any given instant of time. So that change is what we are basically looking at, and that can be very easily related to some of the other fundamental concepts that we'll be dealing with when we are relating stress to strain through the stress strain constitutive matrix, an extended form of the Hooke's law to apply for composites as well, in terms of a matrix now instead of just a single quantity E. That matrix that we are having can then be used to formulate the strain energy for a linear material in terms of a quadratic form of the strains. Now that strain energy is a scalar quantity, and those concepts that we understand as part of the fundamentals in the initial few lectures of the course will then be very handy in understanding how that strain energy changes as the crack grows, in understanding the fracture mechanics concepts. The fourth thing is fatigue, where we are looking at cyclic loads. So how we deal with that in this course is very simple. We'll just look at how when you have very simple cyclic loading situations, how the composite structure responds to that. And as you keep increasing the number of cycles, how the strength slowly reduces, and how this can probably be best dealt with in terms of the original design of the material and the structure to delay the fatigue failures or to avoid them. And finally, finite element analysis, the way we will expose you to in this course is through a very brief introduction to the implementation without going into the coding aspects, by using again what we studied as part of the fundamentals through a consistent elasticity approach. Many people, the way they introduce finite elements is a very ad hoc way, so we'll not do that. We will again stick to the same format that we do in the fundamentals fundamentals where we take a consistent elasticity approach, which is always very, very useful, because then it can deal with stresses and strains in multiple directions, loading and displacements in multiple directions, and they being present simultaneously, and what happens in terms of the overall deformations and their movement towards failure and avoiding that. So that's what we will base our finite element study on, that is a consistent elasticity approach. Then, as I said, in doing that, we will be dealing with multidimensional stresses, strains, and therefore the constitutive law, which is in the form of a matrix. In other words, the stiffness is in the form of a matrix. For linear materials, it's a matrix of constants. For nonlinear materials, that matrix could become a function of the strains. Then we will talk about finite elements from a perspective of displacement as a vector, and therefore represented as a column matrix when its numerical values are given. This is again slightly different from some approaches that other people take in terms of a force-based finite element analysis, etc. We will take a displacement-based one, not also a stress and strain, a kind of an approach, though those would be essential in formulating the energy, strain energy, and therefore coming up with the expression for the strain energy in terms of the strains. But then the strain displacement relationships will be used to eliminate all the strains in the expression for the strain energy in terms of displacement derivatives, and therefore we would have everything expressed in terms of displacement, and then that becomes the only unknown to deal with, and we would solve for that in a numerical sense. So this is used, these displacements will be used in deriving the governing equations for all kinds of loading, including torsion and bending, so that we have an understanding of a simplified structural theories also vis-a-vis the 3D elasticity approach, which is much more generic and therefore gives you the bigger picture. So it's very essential that you have that bigger picture, because then you understand where each one of these details that we learn about fit in. Otherwise, each one of them might seem like completely disconnected from each other. If any questions on this, how we are going to handle the 5 F's in this course?
Sir, hello.
Yes, please go ahead.
Sir, this is Samanvay.
Yes, sir.
Sir, in the finite element part, would we consider in the coding part or the theoretical equations we will be dealing with?
Yeah, we will just be dealing with theoretical concepts and very few equations, because it's a very generic course. So definitely, because you are a PhD into structures, you will be interested in going further into this, for which there will be other courses. So we will only give a flavor for non-structural engineers, so we will not go into coding.
And sir, a very different question.
Yeah.
So, like in the upcoming semesters, in
Yeah.
the aerospace department, there are courses which will teach us the coding part and all.
Correct.
Okay.
Yeah, there are quite a few. So you don't need to, I mean, if necessary, you can take it in parallel with this during this course. You can discuss with your advisor and see if it's essential for your research, whatever is the plan. And then you can choose to take them this semester itself. But also you can take it in the future semesters, and you're always welcome to take courses not just in aerospace engineering department, but also in the civil engineering and mechanical engineering department, where there are quite a few very good finite element analysis courses.
Thank you, sir.
You're welcome. Anybody else? Any questions? Okay, let me move forward. Okay, now let's look at a few ways in which we can classify aerospace structures and their behaviors and their loading situations, etc. So there are many different bases on which you can classify aircraft structures. It could be based on the application. It could be based on the stage of engineering that we are dealing with. It could be based on whether there is a time dependency or not. If there is a time dependency, how? based on the engineering techniques that are involved, based on the type of materials that you're going to use, based on the external load type that is acting on those structures. Then it could be on the phase of the flight of the aircraft. It could be also based on the geometry of that particular structural component and how it is attached to the rest of the aircraft. So let's look at each one of them. So if the classification basis happens to be the application, then the category basically depends upon the kind of vehicle that you're dealing with. It could be an aircraft, it could be a helicopter, it could be a missile, it could be a launch vehicle, it could be a satellite, etc. So of course some of these can cover unmanned or uninhabited aerial vehicles as well, what are known as UAVs, and much smaller versions of that, what are known as micro air vehicles or nano air vehicles, where micro and nano are not in the sense of microns or nanometers, but typically used in a relative sense compared to the traditional sizes of aircraft and helicopters. Now, within each one of these categories, all of which we call as flight vehicles and therefore are under the purview of flight vehicle structures, both the concept as well as the course. So when we are dealing with aircraft, we talk about both military aircraft as well as civil aircraft. The kind of design paradigms are quite different. There's a single entity which governs this certification in the US, for example, FAA. But in the case of India, the military aircraft are governed by DGCA's regulations and the CEMILAC regulations, and the civilian aircraft by the DGCA regulations. So these things are going to be slightly different in terms of the requirements for the design or the analysis. So there are subtle differences which come with respect to the corresponding aircraft structures which go into, let's say, for example, a Boeing 787 as opposed to an F-18 or a Tejas. So again, within the military aircraft, there can be various types. There could be fighters, there could be bombers, there could be transport aircraft, military transport, that is. Each one of them again would have their own requirements. For example, amongst all these three, the fighters would require the maximum amount of maneuvering. So you would go for an unstable design, which means you will have to deal with elastic or aeroelastic instabilities to a much larger extent than you would deal with a civilian aircraft or even other kinds of military aircraft. So then again, bomber, the kind of loads that it needs to take, and once it drops a bomb, the kind of dynamics that results in the release of the bomb, etc. So those are certain specifics which are related to the structural design there as well, and the structures which are related to holding the bombs and then releasing them, etc. Similarly, in the case of the transport aircraft, many of which features of which would be common with the civilian aircraft, but the requirements are a little less stringent. For example, some of the military transport aircraft, you can go with a single engine, but you cannot do that with a civilian aircraft where you have to have multiple engines so that there is a redundancy. When one engine fails, you still have at least some hope of saving the aircraft and the people inside. So those kinds of subtle differences translate in terms of structures, because when you have a single engine where the thrust acts is a single location, whereas with multiple engines acting at multiple locations, and those loads will then redefine the way the let's say the bulkheads on the fuselage or the ribs in the wing are placed, and therefore there are design differences which will come because of that. So it's not just a classification of flight vehicles, but how structures are going to be different because of these different classes of vehicles. Again, in the case of helicopters, you could have conventional helicopters which have a main rotor and a tail rotor for the anti-torque system. There can be a NOTAR kind of a design, as in some of the old McDonnell Douglas designs, where you have airstream going through the tail boom of the helicopter, and then coming out through a fan, which is not a tail rotor, but just that air coming out creates a force in the opposite direction according to Newton's third law, and that creates the anti-torque which is required. So that's called as a NOTAR or a no-tail rotor kind of a design. Again, there could be many other helicopter designs where you have counter-rotating main rotors that you would have probably seen in certain videos, or it could be in tandem, the two rotors which are side by side or one in front of the other, and they are rotating in opposite directions, so that the torque that they create is cancelled out, and therefore they are predominantly producing the lift and the thrust which is required for the helicopter to move. Again, the structural design of the rotor blades, the rotor system, as well as the fuselage, again, is going to be quite different depending upon which type of helicopter that we are looking at. So we may not go into all of those details, but we will touch upon it as and when it is necessary to see what are those subtle differences. Then again, coming to missiles, it could be a surface-to-air missile, air-to-air missile, or a surface-to-surface missile, and many other categories are there in terms of the ranges that they have, like intercontinental ballistic missiles, etc. So again, there are going to be many subtle differences, because the altitude at which they fly, the speeds at which they fly, and where they are eventually going to hit, all these will come into the structural design of the different stages of this missile, the structures that are there, and then of course the separation, the stage separation, and what is involved. We have quite a few people from there's some noise coming. Yeah, thanks. There are quite a few students from ISRO. Can you just mention any of you from ISRO?
Yes, sir.
Yeah.
Yes, sir.
Your names?
Akshay Ranjan Bhatt.
Okay.
Nalin Singh.
Okay, very nice. I remember you from the interviews. Very nice. Good to see you. I think there are a few more, right?
One more is the
Yeah.
Sriram.
Okay, very nice. Okay, so obviously for you, many of these things that I talk about will be very, very preliminary, because you do far more advanced stuff than that. So bear on with me. And I think it will be great if the other students can interact with these three from ISRO to understand some of these aspects in a little more detailed sense. Though not all of you might be in the structures related thing, but I'm sure you would know quite a bit more to help your fellow classmates. So I request you, because this is not just a vertical kind of learning, we need to have a horizontal kind of learning where all of us learn from each other. And so your expertise and experience in these areas should be beneficial to the other students as well. So I really request you to do that and engage in discussions with them. Unfortunately, we are not meeting face to face, but you can have certain online discussions with your fellow classmates using the same platform, Teams or whatever else suits you. So, yes. One of you wanted to respond to that? Okay, thank you. So launch vehicles again could be either sounding rockets or a satellite launch vehicle to a polar orbit or to a geostationary orbit, etc. In the Indian scenario, it is a PSLV, GSLV, various marks over there in terms of the versions. And then the satellites themselves, the geostationary satellites, polar satellites, because the kind of loading, again, you're dealing with there is quite different. You're in space, kind of in vacuum, and the kind of loads that they come on there is very different from the aircraft, where aerodynamic loads are predominant, etc. In this case, for example, if it's a re-entry vehicle, for example, a re-entry module, then you would have to deal with the kind of thermal loads and the high speed loads, aerodynamics later on as you enter the atmosphere. So many complications are there. Again, within the aircraft structure also, dealing with the airframe structure is very different from dealing with the engine structure. Though the physics and maths are all the same, the complications which are there in either case could be quite different. Again, the speed regimes in which they operate are typically divided in terms of the Mach numbers, or the non-dimensionalized speed with respect to the speed of sound at that particular altitude at which you're flying, because speed of sound changes with the altitude because the density of the air changes. So it could be supersonic, which means faster than the speed of sound, subsonic, which means lower than the speed of sound, and most passenger aircraft operating in between these in the transonic regime, typically around 0.8 to 0.9 Mach numbers. So that transonic regime, where it's just about to change over, is also again a very specialized region where the aerodynamic loads are going to be slightly different from how you're going to consider supersonic or subsonic designs. So the aerodynamic design itself is going to be very different. The kind of airfoil cross sections which are used for subsonic are much more rounded leading edges. You could have sharp leading edges, a delta kind of wing configurations for the planform, etc. So that aerodynamic design changes are going to reflect in your structural changes as well. How you're going to design that structure, because the very shape has changed, the very loading has changed. So how you design that semi-monocoque structure for a supersonic, or even more so for a hyperplane, which is going to be of importance in the next few decades, a hyperplane, based on some of the technologies both ISRO in the past and DRDO last month has proved in terms of their hypersonic technology demonstration vehicle. It's not just the technology which is associated with the scramjet there, the supersonic combustion ramjet engine, which is the most critical technology over there, but there are many other associated technologies, including those with structures which are very critical over there too. So how do you come up with those? The kind of heating that might be involved might require you to go to what are known as carbon-carbon composites in certain things, but then in terms of oxidation and the other kinds of environmental degradations, they may not be suitable. So you might need certain coatings for that, etc., or coolings which are in the form of active cooling, etc. So the structural design goes a paradigm shift, moving from subsonic designs to hypersonic designs. And as I mentioned in the previous class, if it's very low subsonic and very small sized aircraft, you don't even need to go for a semi-monocoque construction. No need of stiffeners. You just go for a thin shell kind of design, and that should be good enough for a very small, slow speed aircraft. So some of the micro air vehicles or nano air vehicles can do with that kind of a design too. So that's the classification as far as the application is concerned. Then we look at the classification of aerospace structures on the basis of the engineering stage that we are involved with. In the analysis stage, the kind of things that we are dealing with is we already have an existing aircraft. We have the geometry of a particular wing. We have the geometry of a particular component in the wing, let's say a spar, which is an I section. And then we are trying to analyze that. So the geometry is already in place, the kind of loads that are estimated already in place, and then we try to analyze for the kind of deflections or deformations it will undergo, the kind of stresses that are developed, and which are the critical areas, etc. On the other hand, when you're doing a design problem, you don't know a priori what is the shape of that component. The aerodynamicist might tell you the shape of the airfoil as a whole, so you know the outer shape of the structure of the wing, but then inside what goes into it, what is the thickness of the wing panels that you want to have on the top surface, on the bottom surface, how they are going to change along the length of the wing, because throughout this span you do not need to have that kind of a thickness, because the stresses are going to be much more closer to the root where the wing is attached to the fuselage, and therefore at that location you might need a thicker kind of configuration. So this kind of tapers down in terms of ply drops, etc. So how do you design that? So the geometry and also the stiffeners. So what all stiffeners you're going to place, the stringers, how many stringers, what is the cross-sectional geometry of that stringer in both in terms of the shape as well as the sizing, then the spars, what is the spar web thickness, etc., what materials you're going to use there. So in the case of analysis problem, all those are known quantities, whereas here those are unknown quantities. It kind of becomes a reverse problem, but the same mathematical models many times can be used for this purpose as well. And then the design will then lead to optimization studies as well. So it's going to be quite different in terms of how you're going to implement those same mathematical models, because there can be a interchange between the knowns and the unknowns of the problem. So you might have to invert some of those equations. In many cases, that's not a trivial matter to just invert the equation, because these could be highly coupled equations and non-linear too. So if they're linear equations, even if they're coupled, then you know you can probably invert the matrix as long as it's not singular, and take care of those design problems. Next is when you're dealing with stability. Again, it's a whole different paradigm in terms of how you're going to approach the engineering structures from a structural engineer point of view, or even an aeroelastic engineer point of view. Then something which is becoming very, very critical these days, which was not given so much of consideration in the past, is in terms of the health of the structure. Earlier, you just designed it with a certain factor of safety and left it, but now you're trying to monitor that health. And you have what are known as health and usage monitoring systems, abbreviated as HUMS, HUMS. Health and usage monitoring systems, not only for the structure but for the many other aircraft systems as well. But if you're looking at health of the structure, we have what is known as structural health monitoring, or SHM, and there you try to understand the damage mechanics, both in terms of the fracture mechanics, which we will touch upon, also in the case of the composites, the delaminations, fiber matrix debonding, fiber breakage, matrix cracking, etc. And those will then help us to understand how we can estimate the life. This is prognostics. Basically, when you're going to a doctor, he's using a stethoscope, he's using, let's say, a sphygmomanometer to test your blood pressure, or an ECG machine to look at your electrocardiograms, etc. So these are all basically diagnostics which tell you what is the current health situation of your body. Similarly, there are certain sensors which are needed to sense the health of the structure in terms of what kind of deformation it goes through, what kind of stress levels it goes through under a typical loading situation. And then based on that, what kind of damages are occurring or growing, and can we estimate the life of the structure and therefore of the aircraft as a whole. So those are the kind of things that you look at in estimation. And then we go a step further, and from the we look at the prognostics, which is basically looking at what is the takeaway from that in terms of the remaining life, and how we can extend that life, let's say through a composite patch repair or something else, replacement of a particular component, how quickly that needs to be replaced, etc. So all those life extension programs are very common, especially in the case of military aircraft, and also to some extent in the commercial scenario as well. The third kind of classification is in terms of the time dependency. So though almost all the aircraft structures are dynamically loaded, you can have an equivalent static analysis, because you can think of the steady state analysis. For example, an aircraft is cruising, which means that it's maintaining its altitude and it's maintaining its speed. Then most of the loads are kind of steady state. Even though the aircraft as a whole is moving, it's basically kind of, for the most of the structural analysis, you can do a static analysis. So that gives a lot of insights even for doing the dynamic analysis later on. So again, within the dynamic analysis, there is problems of vibration, impact, and fatigue. And within vibration, you could have free vibration. Without any load, it's vibrating. That helps us understand the natural frequencies of the system, what are the natural mode shapes, and therefore which kind of frequencies you want to avoid in terms of the loading, and if frequencies approach that, what you need to do. All those kinds of things need to be studied, and free vibration study is essential in order to go to the next level, which is the more realistic forced vibration. In the presence of force, how it vibrates, and how those free vibration characteristics can be used to understand the forced vibration better. And then random vibration. For example, we talked about the gust in the previous class. So those kinds of situations can lead to random loading and therefore a random vibration. And how do you deal with those kinds of situations where you do not have a proper understanding of the actual loads which are coming, but over a certain range and in terms of their time history or behavior. Then, so those are all a little easier to deal with compared to impact problems, which are now happening at a very, very short instant of time. There is something coming and hitting, let's say a bird hit. which is very common in the case of aircraft flying low, especially in airports which are within the city, especially if there are kind of large meat shops or meat factories. Then you see a lot of birds close. So there are certain restrictions in terms of avoiding certain kinds of industries or businesses around an airport. But still, nonetheless, you see many times these birds get in. So how, for example, when this bird gets in, especially into the engine and hits a compressor blade or a fan blade, and then that can it might seem innocuous because the bird seems soft material, and also it may not be very heavy unless it's a large bird, but in spite of that it can cause predominant damage because of the speed at which the aircraft is flying. It's the relative speeds which are important, and then it has this high RPM at which it is rotating. So it's a combination of all of these which can create an issue, and sometimes there could be a blade out. Of course, the design takes care of all of these not happening for typical kinds of such ingestions, how to avoid that. So those are all things that impact can study. There are many other types of impact. The bird hit is only one of them. It could be just that the maintenance engineer is using certain tools or drops a hammer on the aircraft that creates an impact damage which may barely be visible. So on an inspection, on a visual inspection, it may not appear. But then you need to do certain non-destructive evaluations to inspect the structure at a certain maintenance frequency, which is specified typically by the manufacturer and the maintenance engineers. So that schedule, you typically will observe those things. So the designing for that impact, and if an impact has already taken place, analyzing that impact situation is something that we would look at in this situation. And then, as we already talked about the fatigue loading, especially helicopter rotor blades, for example, or the turbine blades, but in many other situations as well, even in the case of the aircraft wing, you would have certain levels of fatigue, and you need to address those issues as well as a structural engineer. Then coming to the time dependency, we have seen next is the engineering technique that we use to study that. We already saw the finite element analysis, which is basically a theoretical thing, a model which is implemented numerically, right? So similarly, you could have analytical models as well, closed form solutions, which give you a lot of insight. Some of them might be very simplistic textbook kind of formula, but still can give you an exposure. Yes? Somebody had something to say? Yeah. So analytical models as well, but there are more advanced models which are much more realistic today, and that can be of significance as well. So again, depending upon whether that analytical or numerical modeling is starting from a Newton's law perspective, let's say force is equal to mass into acceleration, or moment is equal to the moment of inertia into the rotational accelerations, those kinds of vectorial equations can lead to an equilibrium based approach, whereas an energy based approach, we are trying to minimize a certain functional using a calculus of variations approach, lead to a variational kind of problem. So within theoretical, they're both analytical numerical and variational equilibrium kind of classifications, and many of these coming from a variational approach tend to be much more rigorous and are much more easily dealt with even in a numerical implementation, as most of the finite element analysis codes are also based on variational principles. Then, of course, you need to have an experimental understanding of the theoretical structures, fabricating specimens, testing them, characterizing the material, characterizing the structure, and then the full-scale component level testing, and sometimes a full-scale aircraft testing. Hopefully, some of you attended the lecture by the Airbus expert, the only Airbus expert that we have in India, who talked about full wing kind of testing for one of the Airbus aircrafts, and you saw that how complicated that was. 70 million degrees of freedom to be dealt with. So if we can do that in a numerical sense, well and good, but at the end of the day, a lot of these things have to be verified experimentally, and there there's both ground level testing, ground based equipment which can test the aircraft on the ground, and then there are also flight-based testing, what is known as flight testing, and IIT Kanpur has an aircraft on which they do a lot of these flight testing and get data which is used, and some students can take advantage of that sometime down the line. We are in talks with IIT Kanpur to enable that for some of you. Then in terms of the tests, as I said, there could be destructive evaluations or non-destructive evaluations. So destructive tests are typically on the lab level specimens, sometimes even on the to study the crash worthiness of an aircraft. Some of the regulations require a test which is going to be destructive as well, but most tests on the actual aircraft or aircraft components will be of a non-destructive evaluation. And we have a very profound group of researchers in the aerospace department led by Dr. M.R. Bhatt and Professor Devi Prasad Roy Mahapatra, to some extent Professor S. Gopalakrishnan, who all work in these areas of non-destructive evaluation. So there is a course also on NDE which is offered by Dr. M.R. Bhatt. Those of you interested can, in the more of the experimental aspects, can look into that. Then we have classification in terms of the material type. It could be homogeneous or non-homogeneous, which means from point to point the material is not changing, and therefore the material properties are not changing, which leads to a lot of simplification. And non-homogeneous structures like composite, where the property is changing from one point to another. One point it could be a fiber, another point it could be a matrix. So properties are changing, where we need to deal with a equivalent homogenized structure. Then at a given point, in different directions, if the properties are same, you have an isotropic material. If they are different in different directions, you have an anisotropic material. Again, the material could be linear. In other words, the stress-strain relationship, even if it might be coupled in different directions, it would be linear. In other words, all the elements of that matrix between the stress and the strain relationship are constants. So that's a linear material model. But in general, as the strain increases, you would see that most materials go into a non-linear regime. Especially metals, metal matrix composites. Brittle materials tend to stay linear almost until failure, but there could be exceptions there too. Then coming to another classification of the materials which are used in an aircraft structure, some of them could be elastic, in the sense that when you remove the load, all of the deformations are removed as well, and it comes back to its original shape and size. Whereas in the case of a plastic material, there is certain permanent strain which remains in certain directions, because of which is a permanent deformation. And plastic is just an example for inelastic in general. So you could have various forms of inelastic materials. We'll not go into too much of those details, because most of the regimes in which aircraft will be operating will be in the elastic regime. So that should work for most of it, except when you're dealing with damage mechanics, when certain locations are extended to the inelastic regime, and therefore that model has to be incorporated, inelastic material model has to be incorporated before you understand damage in a more realistic sense. Then again, you could have another classification of materials in terms of conventional materials which are unifunctional, and the multifunctional materials which are not just load bearing but perform an additional function. An example of which is the smart structure that you see over here. So you would have shape memory alloys or piezoelectric materials, magnetostrictive materials, magnetorheological materials, electrorheological materials, etc. Within the piezos, again, you could have wafers or films or piezo composites. So many different materials which are used for specialized applications, but they are not extensively used throughout the aircraft, but in certain locations where they might make a huge design difference in terms of the performance or stability of the aircraft. Then in terms of the external load type, again, you could have differences. And many of the times these are all operating in combination. So there are gravitational loads, of course, for all types of flight vehicle structures. In the case of satellites, the gravitational load might be coming from multiple bodies, not just the Earth, for example, but the moon as well, depending upon what kind of an orbit it is in and how close it is to both these structures. Some of them might be more dominating than the other, but you can have gravitational loads which are varying as the vehicle moves as well. But for most aircraft kind of applications, the gravitational loads are kind of constant at the lower altitudes that we are flying. Then we have the inertial loads, which is like the D'Alembert's force in the Newton's law, where you take the mass into acceleration or the moment of inertia into the rotational acceleration as the inertial loads. When we say loads, it's generalized. It could be either a force or a moment. And those which come due to gust, for example, again are inertial kind of loads. Then you have the thrust from the aircraft engine, which acts as a load for not only the engine components, but then the engine is attached through a pylon to the aircraft wing or the fuselage. Then how that load transfer gets transferred, the thrust transferring apart from the self weight of the engine acting on the component to which it is attached. Then in terms of the turbulence of the exhaust, so the exhaust is what creates the thrust using Newton's third law. When the air which goes in uses the fuel to burn it and then comes out through the turbine and later through the nozzle, it creates a thrust force, a similar kind of situation in a rocket engine as well. But these exhausts can themselves have a certain turbulence, and that can create certain loads as well. And that can be acting on the tail, the horizontal stabilizer of the aircraft, or the vertical stabilizer if they are in the wake of the engine which might be on the wings. So that is a kind of loading we need to take care of. Mechanical loadings like bird heads, and when you're taking off or landing, the landing gear is in touch with the ground during taxiing also, for example, then you need to account for those as well. The frictional loads between the wheels and of the landing gear and the tarmac of the runway surface. Then the aerodynamic loads, of course, the most dominant for a lot of design and analysis situations. Then the thermal loads which are coming because of change of temperature with altitudes, as well as the hot air coming out of the aircraft exhaust, the thermal loads. Then the control loads, which again, depending upon the control systems used, fly-by-wire, etc., for example, could be electric, magnetic, electromagnetic, or hydraulic. There are also redundancy systems where if the electromagnetic system fails, the hydraulic systems kick in. So the servo systems that are involved there, the loads that come from it. And then the aerothermo-servo elasticity that I briefly mentioned last time, where the aerodynamics, thermo loads, and the control loads are all operating simultaneously along with the structural behavior of the material itself. Then in terms of the flight phase, again, you have classifications. At takeoff, there are certain kinds of loads which are acting where the before the actual takeoff happens, you would have the ground loads, and then as the takeoff is happening, because all of your flaps and ailerons are also deflected downwards, and therefore the kind of loads that are created because of the high lift coefficient quite different. Again, next you go to the climbing phase, where there are no ground loads, but the atmospheric loads are varying quite a bit, so the dynamics coming because of that, and the ground effects that are there. And then eventually when it cruises, then if it is maneuvering, even simple maneuvers or more complicated maneuvers in the case of fighter aircraft, all of those are going to result in very different kinds of structural design parameters, depending upon which of them is going to dominate a particular component's design. One component might be dictated by a particular maneuver. Another component might be dictated just by the landing. Another maybe by the descent, etc. So it depends on design to design, So we need to consider all of these phases that an aircraft would typically operate in and take the most critical phase for a particular component and make sure that the material choices that we make, it could be multiple materials, all the material choices that we make, the geometric choices that we make, the joint choices that we make between multiple components, all these will be able to handle that most critical phase of the flight. And finally, in terms of the classification, because of the geometry of the undeformed shape of the structure, because the geometry also evolves or changes with the load, it deforms. But even when it is not loaded at all, there is a certain geometry it has. For example, the wing has a certain airfoil cross section, it has a particular planform geometry, etc. So that undeformed geometry, based on that, we classify the structural components into three categories: 1D, 2D, and 3D. 1D, where the one of the dimensions, which is the length of the structure, dominates over the other two. 2D structures, where the thickness of the structure is very small, negligible compared to the other two. And three-dimensional structures, which are more like brick-like structures, very commonly used in civilian or mechanical constructions, but rarely used in a flight vehicle kind of a construction. But we are going into thicker and thicker composites, especially for aircraft engine applications, where we use 3D weaving techniques in order to accomplish ceramic matrix composites through ceramic vapor infiltration, etc. So those kinds of processes would also deal with thicker composites where delamination, etc. is a problem. And there you may not be able to use a 1D or 2D model. You might have to go for a 3D model. So though it is rare, there are certain situations even in aircraft structures where such models are used. And again, when it's 2D, if it's not having any initial curvature, then you can deal with it as a plate, much simpler. And if it is having an initial curvature, like on the aircraft wing, the top surface is basically an airfoil surface, or it is curved. So each panel might look like it is almost having zero curvature, but there is a small curvature. In some cases, like in the leading edge of the airfoil, there might be a very large curvature, and so you do need to deal with these initial curvatures as well. That is, in the unloaded situation, it is curved. That is why it is no longer a plate but a shell. So how do you deal with that initial curvature is what you see here. And then rods and beams, once again, they could be curved in general, and they could be tapered. You could have an I section which is much larger flanges at the root of the wing compared to the tip of the wing. So it is slowly tapering down in thickness. And so these kinds of situations are also one-dimensional structures, but of a little more complicated geometry, but still we can deal with 1D models for that. Again, depending upon whether the dominant load is a compressive, therefore columns, or it could be a shaft if it is a dominant load is a torque, and so you have torque tubes, etc. And bending, you have the box beams within an aircraft consisting of the spars, their flanges and webs, as well as these stringers and the skin of the wing. And then pipe-like structures, etc. So again, all of these are classifications based on the geometry. There could be certain frame-like structures, like the bulkheads in the fuselage, where there's a huge load transfer taking place. For example, where the wing is attached to the fuselage, you'll typically have a bulkhead which ensures that the load transfer is smooth between the wing and the fuselage, so that no concentrated loads causing material failure happen. Then finally, within those, again, you could have within the beams, you could have solid beams or hollow thin-walled beams or hollow thick-walled beams. So that kind of a classification is also possible. And again, the techniques that deal with each one of them is quite different, because we can take advantage of certain things, and sometimes complications arise. We think a thin wall might be simple, but thin wall leads to a lot of complications because of the larger deformations, displacements, and rotations that are involved, which makes the strain displacement relationship nonlinear. In other words, these geometric nonlinearities can make the model extremely complex. Then again, in terms of the 1D structures, you could have cross sections which are symmetric, cross sections like in the case of an eye section, an asymmetric cross section in the case of a channel cross section. It might be symmetric in one direction but asymmetric in the other direction. Then you could have axisymmetric, like in a shaft, which is a thin walled circular shaft, or it could be even a rectangular box beam which is within, let us say, the wing. It's called as the wing box. So these kind of structures could be there where you can utilize certain symmetries that are involved at certain situations. Then you could have sections which are closed sections, like that box beam that I talked about, where the torsional stiffness is very large, and so the torsional deformations are low, and therefore a linear model might be good enough. In open sections like the C section or the T section or the I section that you have, the torsional stiffness is very low. The bending stiffness in one of the directions could be low, and therefore non-linearities become very critical to deal with. So with this, I think I come to the end of today's class. So if there are any questions, I'd be happy to deal with them.
Sir, good afternoon, sir.
Yes,
This is Franklin here.
Yes, Franklin, go ahead.
Sir, apart from this topic which we have discussed, sir, how do we submit our assignments?
Rajesh, Renuka and Vignesh are your teaching assistants. You can just search for their names by entering in your Teams or in your Outlook, and you could email it to any one of them or all three of them, and they will take it forward. There are also ways of uploading it to the Teams itself. So if you're not familiar with this, for the first assignment, you could probably email it to them. But going forward, it might become too much of disk space for them to handle that. So it would be advisable, because we have 1 terabyte each for the for everybody on the Teams system on the SharePoint. You could share it with that. So if Vignesh or Rajesh or Renuka can probably give some insights to the students in terms of how they could upload their assignments onto the Teams platform. Are you there?
Yes, sir.
Yeah.
So we'll let them know.
Sure.
Whenever the assignments are there.
Yeah, send a chat message to which goes to everybody, so that everybody is aware of that. For the first assignment, we'll make an exception that they can send it by email to you as well if they are not able to upload it. But from the next assignment onwards, it has to be on the Teams system. Yes, Renuka?
Sorry, sir, I lost the connection. So.
Yeah, so I was just saying that they can probably submit it. Those of them who do not know how to submit it on Teams can do it over email for this assignment, because it's due day after tomorrow. But others who know, let them submit it on the Teams platform. And over time, I think it's important from the next assignment onwards, everybody learns how to submit it over the Teams using the files section that is there. Vignesh, if you can probably walk them through this by just sharing your screen, that would be great also. Vignesh, are you around? He's probably not. So anyway, so just set up a meeting, Vignesh. Oh, Vignesh, you're there. Yeah, can you just unmute yourself?
One second. Can you hear me?
Yes, we can.
Yeah. So they can actually CC all of us, Rajesh, me, and Renuka, and send the first assignment. Or as you said, they can just attach it in the chat.
Yeah.
Right?
Sure.
So all three of us could see it.
Yeah.
Attaching chart would after that it may become difficult. Rather, we will say some subject line, so that every mail will come to one folder.
Yeah.
So that would be easier for looking at assignments.
Yeah.
We
First
will
thing is,
convey
the first thing is the assignment file format should be with your name, the course code, the name, and the SR number. And yeah,
Sure.
that would be sufficient.
yeah. So that would be a better file format, and that's the thing. Yeah. So they can first send I think sending by mail would be better, right? Rajesh, your take?
Yes. For that, we'll provide some subject line for the mail so that every mail will come to one particular folder, so that it won't miss somewhere in the mail list.
Yeah, I wanted to suggest that we can create an Outlook group of the course. So in that group ID only, they can send all the assignments.
Perfect.
that would be one
That's also
particular
fine.
mail ID.
So
That's also-
one, yeah. So yeah, that's also fine. So one group with all three of us inside, and they can just send their attachments to that group. Yeah. Yeah, probably we can send a mail by the end of the day, and it would be better for to send an Excel sheet with the name of the students, their SR numbers, and whether they are crediting or auditing the course.
Okay, we'll float that. Create some spreadsheet and we'll float it. Then they will fill it.
Yeah.
Probably
So,
we'll do it in the afternoon.
yeah, and their so at the moment, so we can put it in the teams, and once we get the mail addresses, we can then form a group depending on that.
Okay.
Yeah. Fine.
Yeah.
Excellent. Thank you. Are there any further questions? Okay. Thank you then. I'm sorry for overshooting the time once again because we started a little late, so had to do that. Thank you, and see you on Tuesday. And good luck with your other assignments. Hope many of you are taking advantage of the Vaibhav sessions because I'm sending the links on the Teams platform as well. So you can attend any sessions of interest to you. There are quite a few related to structures. There was one yesterday, one today in the aerospace regime, which is also about structures, and tomorrow as well. So these three are things which will give you a lot of insight into the current state of the art in this particular area. And I'm also sharing links of other verticals, non-aerospace verticals as well. Some of you might have interest in those as well. So please feel free to attend whatever your time and interest permits. Okay. Yeah.
Thursday we are having class, right?
Oh yeah. Sorry. This Thursday we'll have a class. So we'll meet on Thursday. Yeah. And also I request Rajesh, Renuka, and Vignesh to share the load so that you're not kind of duplicating your efforts. Maybe you three can have a joint online meeting and then decide how you're going to go about these corrections so that you're not kind of repeating each other's work.
The assignment is supposed to submit by this Thursday, right, sir?
That's correct. So it can be till the end of the day on Thursday. So that's Thursday, Friday, midnight. Till that point of time, you can submit.
Okay.
Yes, sir. We will be discussing.
Yeah.
Myself, Rajesh, and Renuka.
Yeah.
We've already started discussing. So
Okay.
we'll be discussing on what to do, and we'll do it.
Sure. Excellent. Thank you very much, and goodbye to everybody.
मृत्युंजय मंत्राः
त्र्यंबकं यजामहे सुगंधिं पुष्टिवर्धनम् उर्वारुकमिव बन्धनान् मृत्योर्मुक्षीयमामृतात् एते सहस्रमयुतं पाशा मृत्योर्मर्त्याय हन्तवे तान् यज्ञस्य मायया सर्वान् वयजामहे मृत्यवे स्वाहा